Okay, let's unpack this. Ever stare up at the night sky and wonder if the Big Bang was really it? Like the absolute, nothing before it starts.
It's a wild thought, right?
Totally. Because, every beginning we know usually has a before.
Yeah, like the setup before the punchline.
Exactly. The band practices before the concert, the seed before the flower, that awkward first date before, well, something hopefully less awkward.
Right.
So the universe just, bam, appearing from absolutely nothing. It feels a bit abrupt, doesn't it?
It certainly challenges our everyday intuition.
So today we've got some seriously mind-bending ideas about what might have been, well, before the bang.
And it's fascinating because our standard model, the one cosmologists use day to day, it works incredibly well.
Oh, absolutely, for describing the universe now.
Right. Explaining the cosmic microwave background, how elements formed. It's been hugely successful.
When you try to wind the clock all the way back to that initial Big Bang singularity,
that's where things get dicey. This point of infinite density, infinite temperature, infinite curvature.
our map just kind of dissolves.
Pretty much. Our current physics sort of breaks down there.
Exactly. It's like the cosmic GPS suddenly says, recalculating, error, end of known universe.
Yeah.
And that always makes me a little twitchy.
Understandably.
Is that a real full stop, the actual creation event? Or is it just where our current physics throws up its hands and says, too weird, man?
That's the core question.
So buckle up, because our mission today is to peek behind that curtain. We're diving deep into the possibility of a universe before the Big Bang.
And we'll be leaning on some pretty advanced cosmological concepts.
Especially those bubbling out of string theory.
Yeah.
Right? We want to understand why scientists are even asking this question and what kind of truly bizarre possibilities they've cooked up.
It connects to a bigger pattern in physics, really. Our best theories often have limits, places where they predict nonsense, like infinities.
Like singularities.
Exactly. Think back to classical physics predicting atoms should collapse. Electrons spiraling into the nucleus, a singularity.
Right, until quantum mechanics came along.
Precisely. Quantum mechanics revealed new rules at the atomic scale that prevent that collapse. Problem solved.
And there's that other one, the Rayleigh-Jeans thing, predicting infinite energy from a hot object.
The ultraviolet catastrophe, yeah. Another singularity averted by quantum ideas, specifically Planck's constant.
So singularities often signal we're missing something, that our theory is incomplete at those extremes.
They're signposts saying, go deeper. Your current understanding ends here.
Okay, so this infinitely squished, super hot, ultra-curved point we call the Big Bang. Maybe that's not the literal genesis, but more like a cosmic speed limit sign.
Warning, physics as you know it breaks down ahead. That's a good way to put it.
And I always think about that neutron decay analogy. A neutron exists, right? It has properties, a history. Then it decays into a proton, electron, and neutrino.
A significant event, definitely.
Yeah. But the decay doesn't mean the neutron didn't exist a moment before. It wasn't created from nothing at the moment of decay.
An excellent analogy. The decay is a transition, not a creation ex nihilo.
So why should the Big Bang automatically mean the universe popped into existence with zero backstory? Okay, let's really dig into this before. Why doubt general relativity right at the start?
Well, general relativity is Einstein's masterpiece for gravity, no doubt. It's passed every test we've thrown at it. But those tests are mostly in regimes of, relatively speaking, lower energy densities, temperatures, and curvatures.
Compared to the Big Bang itself.
Oh, vastly lower. As we approach the Big Bang, we enter the Planckian regime. We're talking energies around 10 to the 19 GeV, temperatures and densities that are just astronomical.
I'm way off the charts where we actually tested GR.
Exactly. And at those scales, quantum effects must become important, even for gravity. General relativity is fundamentally a classical theory. It doesn't incorporate quantum mechanics.
It doesn't speak the quantum language.
Precisely. So to describe gravity in that ultra-extreme early universe environment, we almost certainly need a theory of quantum gravity.
Which brings us to string theory.
Potentially, yes. String theory is one of the leading candidates for a quantum theory of gravity.
And the basic idea is, instead of point particles, everything's made of tiny, vibrating strings. Sounds simple, but I bet it's not.
The core concept is that shift from zero-dimensional points to one-dimensional strings as the fundamental constituents. And yes, the implications are incredibly complex and far-reaching.
But how does replacing dots with loops help us go before the Big Bang? Tell me about duality. Sounds almost magical.
It is a bit mind-bending. Duality is a profound symmetry in string theory. It essentially says that two very different-looking physical situations,
Oh, boy.
Like, say, a universe that's physically very large, described by one set of string theory equations, might be exactly equivalent, physically indistinguishable, from another universe that's incredibly small, described by a different set of equations.
Hold on. Big is the same as small.
In certain contexts within string theory, yes. Or a universe where forces are very strong could be dual to one where forces are very weak. They're just different mathematical descriptions of the same underlying physics.
Okay, that's weird. How does that relate to expansion and contraction?
This is the crucial part. Duality can link a universe whose size, let's call it RT, is expanding,
Like ours.
to another description where the relevant scale behaves like effectively 1 over RT. So as RT gets bigger, 1 RT gets smaller.
So expansion in one picture is linked to contraction in the dual picture.
Sort of, but it's more subtle. The key insight for the pre-Big Bang idea is that our current universe, which is expanding and becoming less curved,
Flatter,
might be dual to a pre-Big Bang phase that was also expanding, but with increasing curvature.
Wait, expanding but getting more curved? How does that work? Like blowing up a balloon but making it wrinklier.
It does sound counterintuitive. The engine driving this, according to the theory, involves another key player from string theory, the dilaton.
The dilaton. Okay, what's that?
You can think of the dilaton field as controlling the overall strength of gravity, like a cosmic volume knob for the gravitational force.
And duality affects this knob.
Yes. Duality transformations change the value of the dilaton. In our universe today, gravity's strength seems pretty constant, so the dilaton is probably stable or changing very slowly.
But in the before times.
In the pre-Big Bang scenario, the theory suggests the dilaton was increasing with time.
So the gravity knob was being turned up. Louder and louder.
Effectively, yes. And this strengthening gravity is what causes the curvature of spacetime to increase, even while the universe is expanding in terms of scale factor.
Starting from almost zero gravity.
The picture is a universe beginning almost empty, almost flat, with a very weak gravitational coupling, meaning a small dilaton value.
Okay, so pre-Big Bang. Universe expands, dilaton grows, gravity gets stronger, curvature increases.
Exactly. The Hubble parameter, measuring the expansion rate, also grows, but the Hubble radius, which is related to the curvature scale, actually shrinks.
So distances get bigger, but the fabric of space-time itself gets more tightly wound, more crinkled.
That's a good way to visualize it. Increasing curvature, shrinking Hubble radius.
But surely that can't go on forever. You can't just keep cranking up the curvature infinitely.
Precisely. String theory itself suggests a limit. When the curvature reaches the characteristic string scale related to the fundamental size of the strings themselves, L's, the description should change.
Because a curve tighter than the string size doesn't make sense.
Something like that. The idea is that physics should prevent the curvature from becoming arbitrarily large. It should hit a maximum, perhaps related to this string length L's.
And then what? Does it bounce? Or transition?
It's expected to transition. The curvature growth stops and likely begins to decrease, potentially matching onto the standard Big Bang expansion we know.
Okay, so this pre-Big Bang phase. Expanding, increasing curvature, strengthening gravity, up to a stringy limit. Now, what about the horizon problem? The standard model's puzzled about how the universe got so smooth.
This pre-Big Bang scenario might offer a neat solution because it starts almost flat.
Low initial curvature.
The initial particle horizon, the distance light could have traveled, would have been enormous, much larger than in the standard hot Big Bang beginning.
So distant regions could have communicated and smoothed themselves out before this increasing curvature phase really kicked in.
Exactly. The uniformity could have been established way back then in that initial, nearly flat, large horizon state.
That is clever. Okay, so in this view, the Big Bang isn't time zero. It's more like a phase transition.
A transition, yeah. A handover from this pre-Big Bang phase of increasing curvature and coupling to the post-Big Bang phase of decreasing curvature and constant coupling that we observe.
Not the origin, but a pivotal moment of change.
Precisely. The bang is the transition itself.
Mind blown. But,
Exactly.
yeah. Okay, big question. Evidence. Can we see anything from before this transition? Any fossils?
That's the multi-trillion-dollar question, isn't it? A direct observation is, well, incredibly difficult, maybe impossible, but there might be indirect messenger. Gravitational waves.
Ah, ripples in space-time. We're finally detecting those.
Exactly. And that transition, going from an increasing curvature, high-energy phase to the standard expansion, That must have been incredibly violent.
shaking spacetime like crazy.
It would likely produce a background, a bath of gravitational waves, relics from that transition.
Okay, but standard inflation also predicts gravitational waves. How would these pre-Big Bang waves be different?
The key difference is the spectrum, how the wave energy is spread across different frequencies. Standard inflation happens during a phase of roughly constant or decreasing curvature.
Right.
That tends to produce a gravitational wave background that's either scale invariant, flat spectrum, or slightly hilted, meaning less energy at higher frequencies.
Okay, flat or decreasing energy with frequency for standard inflation. And the pre-Big Bang waves.
Because they're generated during a phase of increasing curvature and energy density, the prediction is an increasing energy spectrum with frequency, more energy at higher frequency.
A rising spectrum. That's a very specific fingerprint.
It is a clear distinction from the simplest inflationary models.
Have we seen any hint of that rising spectrum yet? With LIGO, Virgo, K-GRAW.
Not directly, no. We haven't detected any primordial gravitational wave background yet, let alone one with a rising spectrum.
But we have limits, right? From things like the cosmic microwave background.
Yes, absolutely. Observations of the CMB's polarization patterns, for instance, put upper limits on how strong any primordial gravitational wave background can be across various frequencies. These pre-Big Bang models have to respect those limits.
So the signal, if it exists, is below our current detection threshold.
Correct. It's an incredibly faint signal we're looking for. But future experiments offer hope.
Like LISA, the space-based detector.
Exactly. LISA will be sensitive to much lower frequency gravitational waves than ground-based detectors. These lower frequencies probe earlier times in the universe's history.
So LISA might have a shot at seeing these echoes from before the bang, or at least constraining the models further.
That's the hope. Detecting any primordial background would be revolutionary, but finding one with that characteristic rising spectrum predicted by pre-Big Bang scenarios, that would be game-changing.
Absolutely. Okay, but let's revisit that transition. Going from increasing curvature and gravity getting stronger to the standard Big Bang. That still sounds tricky. Doesn't the singularity problem just pop up again?
It's definitely a challenge. You're right. Just naively evolving the pre-Big Bang solution forward, you still run into extreme conditions where the classical description likely breaks down.
So quantum effects have to save the day again.
Almost certainly. We need quantum gravity effects to properly describe that transition phase. Things like back reaction.
Particles affecting the geometry.
Yes. And also corrections specific to string theory, often called alpha prime corrections. These account for the fact that strings aren't points, they have a finite size.
And that size matters when space-time gets super crumpled.
Exactly. At extreme curvatures, near the string scale, you can't ignore the stringiness. These effects might fundamentally alter the dynamics, smoothing out the transition, maybe avoiding a true singularity altogether.
Leading to maybe a bounce instead of a singularity.
A bounce is one possibility explored in related models, yes. Or just a smoother quantum transition from the pre-Big Bang phase to the post-Big Bang phase.
How does that compare to the idea in some standard inflation models where the universe tunnels from nothing?
It's conceptually quite different. The tunneling from nothing idea usually involves quantum cosmology based on general relativity, where the entire universe wave function emerges from a state of no geometry or nothing.
A true beginning from quantum foam, sort of.
Whereas in the pre-Big Bang string cosmology context, it's often viewed more like a scattering or reflection process. You have an incoming state, the pre-Big Bang universe described by the Wheeler-DeWitt wave function in string theory, hitting the high curvature region.
The transition point.
And then evolving into an outgoing state, the post-Big Bang universe. It's more like a transformation of an existing quantum state rather than creation ex nihilo.
Okay, so less poof, universe appears. And more universe changes its quantum state dramatically. That feels slightly less metaphysically jarring, maybe?
It grounds the beginning within the dynamics of the theory itself rather than requiring an external creation event.
You also mentioned, and I hesitate to ask, pairs of universes being created.
Ah, yes. That delves into even more speculative territory called third quantization.
Third quantization. We just got used to quantum mechanics.
Small chuckle. It's basically applying quantum field theory principles to the wave function of the universe itself in some highly theoretical explorations within this framework.
Brace yourself.
It suggested that the initial state, the string perturbative vacuum, could decay by producing pairs of universes, kind of like particle-antiparticle pair creation.
So the vacuum spits out universe-anti-universe pairs.
That's the rough analogy. One might collapse towards a singularity, while the other expands into a post-Big Bang phase like ours. Again, extremely speculative, but it shows the kinds of places these theories can lead.
Wow. Okay, let's,
Yeah.
let's gently step back from universe pair production for a moment.
Oh.
The dilaton. You mentioned it earlier, controlling gravity's strength. Does it do anything now? Could it be dark energy?
That's actually a very active area of research. The dilaton, or fields like it arising from string theory, are considered potential candidates for quintessence, a dynamic form of dark energy.
So dark energy wouldn't be a constant, like Einstein's cosmological constant, but a field that's changing.
Exactly. The idea is that after the Big Bang, quantum effects could create a potential energy landscape for the dilaton.
Like a hill it can roll down.
Precisely.
Yeah.
And if it's slowly rolling down this potential hill, its energy density could mimic dark energy and drive the current accelerated expansion.
Could that help with the cosmic coincidence problem? Why dark energy is taking over now?
It might. Depending on the shape of the potential, the dilaton could evolve in such a way that its energy density becomes comparable to matter density only recently, or in scenarios called coupled quintessence.
Where it talks to dark matter.
Yes, if the dilaton interacts with dark matter, it could potentially cause their energy densities to track each other over cosmic time, making the coincidence seem less coincidental.
So the dilaton might be connecting gravity, the pre-Big Bang, and dark energy and dark matter. That's quite a workload for one field.
It's a compelling theoretical possibility, linking different cosmic epochs and mysteries. And different dilaton scenarios predict different futures for the universe's expansion.
Which means they're potentially testable with better observations.
In principle, yes. Precision cosmology could distinguish between a true cosmological constant and a dynamic field like the dilaton.
Okay, one last foray into the weirdness. Brain cosmology. Extra dimensions.
Right. String theory generally needs more than 3 spatial dimensions. 9 space plus 1 time is common for superstring theory.
So where are they?
Brain cosmology offers one picture. Imagine our entire 3-dimensional universe is a surface or membrane, a 3-brane, floating within a higher dimensional space, the bulk.
Like a slice of bread in a loaf.
A common analogy, yes. And the idea could be that most forces, electromagnetism, the nuclear forces, and the particles they act on, are stuck on our brain. They can't leave the slice.
But gravity can.
Gravity, in some models, might be able to propagate into the bulk, into the extra dimensions. This could explain why gravity seems so much weaker than the other forces, because its influence gets diluted by spreading out into more dimensions.
That's elegant, actually.
Hmm?
And does this connect to the early universe?
It can. Some models propose that the Big Bang itself might have been triggered by the collision of 2 brains in the bulk, or maybe interactions between brains and anti-brains driving an early inflationary period.
Brain collision sparking the cosmos. It's like a multi-dimensional car crash starting everything.
It provides alternative mechanisms for generating the conditions we see in the early universe. There was even a lighthearted comparison someone made.
Oh.
Comparing the emergence of the universe from the string perturbative vacuum, perhaps via brains, or the pre-Big Bang transition, to the description in Genesis. Let there be light. A bit tongue-in-cheek, of course.
From the vacuum to the Big Bang. Quite a story. Okay, so let's try to wrap our heads around this journey. We started questioning if the Big Bang was truly time zero.
We looked at how standard cosmology points towards a singularity, but how singularities often indicate the limits of a theory.
Which led us to quantum gravity and string theory, with its vibrating strings, mind-bending duality.
And the crucial role of the dilaton field, potentially driving a pre-Big Bang phase of increasing curvature and coupling.
A phase that could solve the horizon problem and might have left detectable gravitational waves with a unique rising spectrum.
Though detecting them is a huge challenge, we also saw how quantum effects are needed for the transition itself.
And how the dilaton might even be playing a role today as dark energy, possibly connected to dark matter.
And finally, we dipped our toes into brain cosmology, the idea of our universe as a membrane in higher dimensions.
Phew, it's a lot. And the bottom line is, the question of what came before the Big Bang is still wide open.
Very much so. These are theoretical frameworks, incredibly powerful and mathematically rich, but still awaiting definitive observational confirmation. The search for those gravitational wave relics or other cosmological signatures is crucial.
So, if the Big Bang wasn't the absolute start, what does that really mean for time? Is our universe just one chapter, maybe one cycle in an eternal cosmic saga?
That's the ultimate philosophical implication, isn't it? Does time itself have a beginning, or is our observable universe just one phase within a much larger, possibly timeless reality?
Definitely food for thought next
Yep,
time
good.
you're looking up at the stars. If this dive into the before has got you thinking, I really encourage you to explore more cosmology, string theory, the hunt for gravitational waves.
Hmm.
It's an amazing frontier,
Absolutely. What we've covered is just scratching the surface of some incredibly deep and active areas of research.
a vast and truly awe-inspiring landscape indeed.